So we continue with the propagation of sound waves, and we are on speed of sound in different media. It is a common experience while standing at some distance from a blacksmith that when a blacksmith strikes his hammer on his iron piece, the sound produced on striking the hammer is heard a short while after the hammer is seen striking. Similarly, the sound of the cracker is heard only a little later than it is exploded when the flash is seen. This indicates that the sound does not reach us instantaneously, but it travels in the medium with a definite speed, and it takes some time to reach us from the place where it is produced. Yeah, it's a very common experience. You will see the lightning first, and then the thunderstorm is heard. The thundering of the lightning is heard later. Similarly, the firecracker explodes first, and then you hear the sound of the firecracker. So वैसे blacksmith का भी example दिया that you see him strike, but the sound of the striking is heard a bit later if you are standing at a distance from him. So all this tells us that the sound is going to travel at a speed which is a particular speed in a particular medium. So sound does not travel instantaneously, but is going to be taking its own time to travel. So the speed of sound is on the medium depends upon two factors. First is the elasticity of the medium, and second is the density of the medium. So we have got two things over here, that the velocity is going to be dependent on two factors. One is the elasticity of the medium, कि कितना elastic है medium, कि अगर elasticity अगर उसका कम है, then it is going to take time to reset itself, and that's why the speed of the sound is going to become less. Whereas the elasticity अगर ज़्यादा है, तो automatically it is going to come back to its original position faster. That's the thing, that in case of solids, because they are very firm, that's why they come back to its original position faster. Whereas gases it will take some time to come back to its original position. That's why it will be slower in case of gases. And second is density. Yeah, of course, density, more the material medium available, the more will be the propagation of the sound. So that is how it works. The speed of the sound in the medium is given by the relationship that V is equal to. Now this part is actually not required. It is not there as a part of the syllabus, but you can know it, you can understand it. This is the density rho. So V is equal to square root of E upon rho, where E is the modulus of elasticity, Young's modulus in case of solids, or bulk modulus in case of fluids. So basically that is the elasticity. The elasticity is going to be measured by a particular modulus. So वो modulus के हिसाब से it will be seen that whether it's a solid or liquid का अलग अलग modulus होता है, तो उसके हिसाब से the Young's modulus के हिसाब से, या तो in case of liquids it is going to be the bulk modulus, which is going to be E, and the rho is the density of the medium. Newton assumed that when sound travels in a gas, the temperature of a gas does not change. The propagation sound is an isothermal change. So when there is going to be sound produced, it does not cause any kind of the heat generated in the substance, because the sound propagation is not so vigorous that uske andar heat generate ho. The vibrations are not so vigorous that it could increase the kinetic energy of the substance drastically, that it will increase the temperature over here. So for isothermal change, Young's modulus of elasticity is equal to the pressure. So it is seen that if the material medium is under or we consider that the Young's modulus or elastic modulus जो है, वो elastic modulus is not going to change, or it is equal to the pressure. Okay, the elasticity will be equal to the pressure if there is no change in temperature. If there is no change in temperature, then E is equal to the pressure P. So E is equal to P. Thus from the equation we get the speed of the sound in the gas as V. Therefore V will be equal to square root of P upon rho. अभी हम लोग को मालूम है that if I increase the pressure, what will happen to density? Density also increases. If I decrease the pressure, the density also decreases. So you can see that the ratio of the pressure and the density is always going to remain constant. फॉर अ गिवन गैस अगर मैंने प्रेशर इंक्रीज किया तो अकॉर्डिंगली ये भी इंक्रीज हो जाएगा, तो इसीलिए दोनों का रेशियो सेम। अगर यानी ये प्रेशर डबल हो गया तो डेंसिटी भी डबल हो जाएगा, तो इट विल अगेन बिकम द सेम फ्रैक्शन। अगर इसको हाफ कर दिया तो ये भी हाफ हो जाएगा, तो फ्रैक्शन स्टिल रिमेन्स द सेम। अकॉर्डिंगली इट इज सीन दैट द रेशियो ऑफ प्रेशर अपॉन density, the ratio of pressure and density is going to remain constant if there is no change in temperature. So for air at normal temperature and pressure, that is NTP, that is pressure is 1.1 to 10 to 5 Newton per meter square, and rho is 1.293 kg per meter cube. So volume V comes out to be 279.5 meter per second. But experimentally, the speed of sound in air is found to be nearly 330 meter per second. Thus, speed of sound calculated by using the above equation is found to be lower than the experimental value. So later on, scientists Laplace applied a correction to the above relation, and according to Laplace, when sound travels in the air during the formation of compression and rarefaction, there is no exchange of heat in the medium. That is, propagation sound is a diabatic change. For an adiabatic change, modulus of elasticity E is equals to rho into P. So when it is going to be for air, then E will not be equal to P, but E will be equal to rho into P. And because of the property over here rho, इसके कारण क्या होता है, the V what we found out, we come out to be at 330 meter per second, which is the actual speed of sound. Now if you take only this part, then V will be coming out as 295.5 meter per second, whereas when you see the actual one, it is 330. So accordingly, we find that the because it's a diabatic change. A diabatic change means no change in the no exchange in the heat is taking place. So उसके कारण the modulus of elasticity is equal to not pressure but is equal to rho into pressure. So hence from the formula we can see that V is equals to rho P upon rho, it will be V will be equal to, so here V is equals to rho P upon delta, that is the density, and the value of delta will be, for air it is 1.4, so rho is equals to 1.4, hence 295.5 into 1.14 will give you 330 meter per second. So that's it. They modified formula, gave the correct value of the speed of sound at NTP, taking it as 1.4 and 1.1 as a pressure, and delta rho as 1.293. We get as, sorry, this is not rho, this is gamma. Sorry, this is gamma, this is not rho. I messed up. This is rho, this is rho, this is gamma. Okay. Anyway, this part is not there as a part of the syllabus. It's just for your understanding. अगर समझ में आया तो ठीक है, नहीं समझ में आया तो भी problem नहीं है, because this is nowhere connected to your syllabus. It's just an extra information. So the speed of sound is different in different media. The speed of sound is more in solid, less in liquids, and least in gases. This part is important. This particular table is what you need to, not table, the block over there is not something which you need to learn. So that is, the speed of sound is different in different media. The speed of sound is more in solids, less in liquids, and least in gases. Since solids are much more elastic than liquids and gases, the speed of sound is nearly 5,100 meter per second in steel, 1,450 meter per second in water, and 330 meter per second in air. The table gives the speed of sound in different media. So air is 330, carbon dioxide is 260, hydrogen is 1270. Alcohol is 1210, turpentine is 1325, water is 1450, copper is 3560, steel is 5100, glass is 5500, and granite is 6000 meter per second. So this is how the speed of the sound is going to be there in different medium. Now examples showing that the speed of sound in steel is more than in air. If a sound is produced at one end of a very long steel bar, two sounds are heard at this one other end. One which reaches the first is propagated by the steel, and the other which is heard later is through air. So if I take a very long steel bar and I hit the one end of the steel bar, at the other end I am going to hear two sounds. One sound will be first, which is traveling from the steel, and the other sound will be heard from the air. So that's why the two sounds are heard. Q2 sound, because they are both traveling at different speeds. So because the one which is going to be traveling faster will be through steel, and the one which is traveling slower will be through air. Similarly, a person living near the railway track often presses his ears against the steel rail to guess whether a train is coming or not. The reason is that the vibration produced by the moving wheels of the train travel faster through the steel rail than through air. So sound is heard through tracks much before it is heard through air. Thus the person, by hearing sound through the steel, gets to an indication of coming of train well before its sound is heard. So if somebody is staying nearby the railway track and if they are going to cross the rails track, and if of course if he's not alone, but I have got many people to cross that thing, then they can always put their ears towards the track. If they hear the sound, that means if they don't hear the sound, that means the train is not coming at all. If they hear a sound, it will sign that the train is quite nearby. But the sound cannot be heard by air, but it can be heard by air, so they know that the train is going to come. So that's why because the train का जो sound है, the vibrations of the train of the wheels is taken in by the tracks, and it is transmitted much faster than that is transmitted by the air. So that's why it is heard easily through the track and later, means faster through the track and later through the air. Now let us see the factors affecting the speed of sound in gas. So in a gas, what would happen? Let's understand that. The speed of sound in a gas is affected by the change in density, temperature, humidity, and direction of wind. Effect of density. From the relationship V is equals to rho P upon L delta upon gamma P upon rho, it is clear that velocity is inversely proportional to 1 upon the density. That is, the speed of sound is inversely proportional to the square root of the density of the gas. The density of oxygen is 16 times the density of hydrogen. Therefore, speed of sound in hydrogen is 4 times the speed of sound in oxygen. So it is seen that the density of the gas, it is going to be inversely proportional. So inversely proportional to the square root of this thing. Now we know that oxygen is denser than hydrogen, and that to 16 times denser. That's the reason that in oxygen the speed will be 4 times less than that of hydrogen, because hydrogen the speed of hydrogen will be 4 times the speed of that in oxygen, because inversely ratio. Okay, it is this way that velocity is inversely proportional to 1 upon rho, 1 upon square root of rho. Okay, अगर ये 16 times है, तो it is 1 upon 16. So therefore it will be 1 upon 4. So that's why velocity of the speed of sound in hydrogen will be 4 times that of speed of oxygen. Speed in oxygen. Effect of temperature. The speed of sound in a gas increases with the increase in the temperature of the gas. The reason is that with the increase in the temperature, the density of gas decreases, and consequently the speed of the sound increases. So we know very well that when we are heating some object, when we heat any particular gas, its density is going to decrease. If the density decreases, we have got this particular condition. If the density decreases, the speed increases. So accordingly, you see that with the increase in the temperature, the density of the gas decreases, consequently the speed of the sound increases. So in fact, the speed of the sound is directly proportional to the square root of the temperature. So we have V is directly proportional to the square root of the temperature, where T is the temperature of the gas in Kelvin scale. The speed of sound in air increased by 0.61 meter per second for each degree rise in temperature, provided the rise in temperature is not very large. So if it is this way, then it will be the velocity of sound at a particular temperature will be equal to 0.61 t plus v0. So that is the velocity at 0 degree Celsius, okay, or velocity at 0 degree Celsius जो भी है, plus 0.61 t. यानी अगर समझो the temperature is 25 degree Celsius, then 0.61 into 25 will be equal to 15.25. So accordingly it will be 330 at 0 degrees plus 15.25, so 345.25 will be the velocity of the sound in air, which is at 25 degrees Celsius. So the speed of sound in dry air is still air at 0 degrees Celsius is 330 meter per second. At 25 degrees Celsius, the speed of sound in the air is V0 plus 0.61 T is equal to 360 plus 0.61 25, that will be 345.25 meter per second. The next is the effect of humidity. Now you know very well, if the humidity is more, then the density is going to increase. So you can see the speed of the sound in air increases with the increase in the humidity in the air, because humid air is less denser than the dry air. The humid air is less denser than the dry air. That's why you can see that, because the vapor density of water vapor is 5/8 times that of the dry air, so it's less than that of dry air. That's why lesser the density, more will be the speed. So the speed of the sound in air is increased with the increase in the humidity in the air. The density of water vapor is about 5.8 times the density of dry air or ordinary temperature. Therefore, increase of moisture in the air tends to decrease the density of air, and the speed of the sound in the humid air is greater than the speed of sound in dry air. In other words, the sound travels faster in humid air than in dry air. So that is about humidity. So we have that velocity is directly proportional to humidity. Okay. And the last one is effect of direction of wind. Obviously, if the direction of wind is with the flow of the sound, then it is faster, and if the direction of the wind is against the flow of the sound, then it is going to be slower. So where the speed of the sound increases or decreases according to the direction of travel of wind. If wind is blowing in the direction of the propagation of sound, the speed of the sound increases, while if it is blowing in the direction opposite to that of the sound, the speed of sound decreases. If V is the speed of sound in still air and W is the speed of wind, the speed of sound becomes V plus W when wind blows in the direction of the travel of the sound, and speed of sound becomes V minus W when the speed blows in the direction opposite to the direction of travel of sound. This is nothing but like upstream, downstream. Downstream में क्या है? It is with the flow. यानी wind is with the flow of the sound, so it is upstream will be X plus Y. Here it is V plus W. If it is downstream, that means downstream में it is V plus W. That means it is with the flow. So direction of the flow of the sound, direction of the wind is same, so it is V plus W. Direction of the sound is this way, wind is coming in this way, then it is going to be V minus W. So that is upstream. For example, the sound of the distant music is quick and loudly heard if it is coming from with the wind. On the other hand, it is difficult to hear if the wind blows in the opposite direction. Now we come to the point where the factor which is not affecting the speed of the sound in gas. So that's the thing. The speed of sound in a gas is not affected by the change in pressure, amplitude, wavelength or frequency of the wave. So it is not dependent on the pressure, amplitude, wavelength or frequency of the wave. So first is effect of pressure. The speed of sound in a gas is independent of pressure. In the formula, V is equals to square root of gamma P upon rho. So this particular formula, I told you earlier that P and rho, if the pressure increases, the density also decreases. Pressure increases, density increases. Pressure decreases, density decreases. So the ratio remains unchanged. P upon rho का ratio remains unchanged. इसीलिए velocity remains unchanged. So the speed of sound in a gas is independent of pressure. In the formula, V is equals to square root of gamma P upon rho. The ratio P upon rho remains unchanged with the change in the pressure. When pressure increases, volume decreases, but mass remains unchanged. So density increases, such that the ratio P upon rho remains constant. For example, if the pressure P of the gas is doubled, volume becomes half and the density becomes double as the mass is constant. As a result, the ratio P upon rho does not change, that the speed of sound in gas is independent of pressure. So it is not dependent on pressure. Second, it is not dependent effect of the amplitude. Amplitude कितना भी हो उससे फर्क नहीं पड़ता. The speed is not dependent on the amplitude. So the speed of sound does not depend on the amplitude of the waveform. Third, the wavelength. कि wavelength the frequency. Higher frequency, low frequency से उसके speed से कोई लेना देना नहीं है. So effect of wavelength or frequency, the speed of wavelength sound does not depend on the wavelength or frequency of the sound wave. So that was about the factors not affecting the speed of the sound in gases. Now let us compare the speed of the sound to the speed of light. So we very well know the speed of light is much higher than the speed of sound. So let's see. There are following 4 points of distinction between the propagation of sound and light. The light can travel in vacuum, but the sound cannot travel in vacuum. Second, the speed of light light wave is 3 to 10 to 8 meter per second in air, which is about 1,000,000 times greater than the speed of sound in air, which is just 330 meters per second at 0 degrees Celsius. The speed of light travels waves decrease in an optically denser medium, where speed of light in water is 2.25 meter per 10 into 10 to 8 meter per second, whereas in glass it is 2 into 10 to 8. So if the density of the medium keeps on increasing, the speed of light keeps on decreasing. Sound में पूरा उल्टा है. If the density increases, speed also increases. While the speed of sound wave is more in solids, less in liquids, and still less in gas. That the speed of sound in steel is nearly 5,100 meters per second, in water nearly 1,450 meters per second, and in air is nearly 330 meters per second. Fourth point, the light waves are transverse electromagnetic waves, while the sound waves in air are longitudinal mechanical waves. So these are the 4 points of differentiation between the sound waves and the light waves. The first one was about the speed. Second one was the material medium required for the sound but not required for the light. The third one was with the increase in the density, the speed of light decreases, whereas the speed of sound increases. And thirdly, light is a transverse wave in air, whereas the sound is a longitudinal waves in air. Now, what are the consequences of this large difference between, and we told you that it is a 1,000,000 times more than, the speed of light is 1,000,000 times the speed of sound. So what happens due to this thing? So it is this way, that thunder and lightning, in thunder, light is seen much earlier than the sound of the thunder is heard, although they are produced simultaneously. Although the clouds are going to dash and the lightning is going to strike at the same time, both are going to strike at the same time, but you will be able to see the lightning first, but the thunder is heard later on. This is because of the difference in the speed of the sound and speed of light. The reason is that light takes almost negligible time in comparison to the sound in reaching us from the place of thunder, because the speed of light is much more, that is 3 into 10 to 8 meter per second, than the speed of sound. Second, when the starter in the athletic event fires a gun, the spectators sitting in the distance hears the sound of fire a little later, while the smoke is instantaneously seen. The reason is again the same thing. So we can see the starter रहता है, उसमें कैसा रहता है, there is a gun, so we fire the gun, so you can see the smoke. So वो gun fire करेगा तो वो gun fire का जो sound है हम लोग को बाद में सुनाई देगा, तो the smoke पहले दिखाई देता है. Similarly, when you go to a stadium to see a cricket match, you will see the player taking a stroke, but you will hear the stroke a bit later. Spectators watching the cricket game hears the sound of a stroke a little later than the batsman is seen actually playing it. This is again the reason is velocity of light is much greater than velocity of sound. Now this is an experimental determination of the speed of sound in air. So it's a very simple thing. What they are taken is they are taken two different places at a distance of 1 kilometer, and then there is at place A, he's going to fire a gun, and he's going to start, as soon as he sees the gunfire, he's going to start the stopwatch, and see within how much time he is able to hear that sound, and he stop the stopwatch as soon as he hears it. और उसके वैसा 3-4 बार करेंगे, and you know the distance, you know the time, so speed is equal to distance upon time, so that is going to give you that suppose he hears the sound after 3 seconds, it is 1000 meters upon 3 seconds, so it will be around 333 meters per second. So that is the experimental verification. The fact that light travels in air about 1,000,000 times faster than sound can be used to determine the speed of sound in air. Experiment: choose two places A and B at a high altitude facing each other at a known distance d apart, say about 1 kilometer, in still air. The distance d is noted. Of course, it should be distance like this. It cannot be a pathway, the distance. अपना यहाँ से यहाँ का distance मालूम होना चाहिए. The distance d is noted. At each place, there is an observer with a gun and a stopwatch. First, the observer at place A fires the gun, while the observer at B starts his stopwatch immediately on seeing the flash of the fire at A, and stops it when he hears the sound of the fire. The observer B, by his watch, thus finds the time interval T1 taken by the sound to travel from A to B. So, he saw the fire, he started the watch, he heard the sound, he stopped the watch. So, he came to know that what is the time taken by the sound to reach that particular place from the point he had fired the gun. Now the observer at place B fires the gun, and the observer at A starts his stopwatch when he sees the flash fire at B, and stops it when he hears the sound of fire. Thus the observer A by his watch finds the time interval T2 taken by the sound to travel from B to A. The average of the two time intervals is T is equal to T1 plus T2 upon 2. This is the time taken by the sound to travel the distance d between the place A and B. The speed of the sound is then calculated by using the formula V is equal to distance upon time del d upon t. Note, in this experiment we measured the time interval 2 times, first for sound to travel from A to B and then from B to A, so as to eliminate the error arising due to the flow of wind. Yeah, because if the wind is going in this direction, the sound will be faster, and when it's going in this side, it will be slower. So when you are taking from A to B and B to A both, automatically you are eliminating the time difference which is going to come due to the wind. However, the speed of sound so determined is not very still accurate, because the personal error of the two observers and the variation in temperature and humidity of the air in between the two places is not considered. So yeah, of course, this is just an approximate value. It cannot be an exact value, because there are so many other factors which are affecting the speed of the sound in air, which you are not considered: the temperature conditions, the humidity conditions. So all these also going to matter. But yeah, this is one of the way we can experimentally find out that what is the speed of the sound in air. So this was about the explanation of the first part of the chapter. Now we are going to move on with the numericals which are there over here for the chapter. So that is the numericals. There are 11 numericals over here. So let's go to the numericals in the next video along with the second part of the chapter.